Okay, good morning, everyone. We are moving on to the next section of the course today. We're finished with population genetics for now, and we're going to be talking about evolutionary game theory for the next couple of weeks. Who's heard of the game theory before? Okay, good, a couple of you. So we'll be thinking about some different ways of modeling evolution. Before, we've been really focusing on the genetics. Now we're going to be focusing on phenotypes instead. And I'll start walking you through this. So, like I said, we've been focusing on this idea of population genetics, which is often thinking about allele frequencies or haplotype frequencies, genotype frequencies, all of these kinds of things, thinking about how they change over time. Ultimately, evolution is all about populations changing over time anyway, but those population genetics approaches are really thinking about those genetic details, things like dominance. We haven't discussed something called epistasis, but that's another kind of thing that's often captured in population genetics models as well. It's about interactions between loci. So lots of those genetic details, we can use population genetics to really kind of delve into understand things like, how strong is selection? How does a particular allele evade into a population? Those kinds of questions. But there are lots of questions that are not particularly well suited to population genetics. For example, if there are particular traits or phenotypes that are characterized by many, many loci. So, for example, things like your height can be influenced both by your genetics as well as by the environment. Having, one allele that determines your height is not a very realistic model. There are also lots of other things. It could be your level of resistance to infection could vary fairly continuously from being, slightly resistant to being very, very resistant. There could be many other things that are not very well captured by those nice, discrete models of population genetics. One area in particular as well is thinking about strategies that individuals or populations may take. That's very important when it comes to things like animal behavior. And this is where things like evolutionary game theory come in and be quite handy. So today, we're going to introduce this idea of evolutionary game theory and how it relates to traditional game theory. There's a couple of things to learn today: payoff and payoff matrices, and pure and mixed strategies. We'll talk a little bit about these things today. Okay, so game theory as an actual sort of more general approach, not evolutionary game theory, originated earlier in the 20th century. It was all about human behavior in economic sense. Okay, so how do we expect individuals to behave in a rational manner? You may have heard of the prisoner's dilemma. Hands up, who's heard of prisoner's dilemma? Okay, some people have heard of prisoner's dilemma, but not game theory, which is interesting. But it's a classic example in game theory. So if you don't know the prisoner's dilemma, the basic scenario is that two people have been arrested for a crime, and they're put in separate rooms, and they're each essentially kind of given a deal that they can snitch on the other one, in which case they can escape. Snitches get stitches, but not in this case. So yeah, they can be set free, and the other person will get full punishment. If they both snitch on each other, then they'll both get a punishment, and but it's lesser. And if they both cooperate with each other in a sense, and so they don't snitch at all, then the prosecution has a case, and so they'll be let free. So that's the basic background of it. And so the idea is, should you cooperate or should you cheat? Should you, that's the slightly more evolutionary perspective, but here, should you defect or should you keep quiet? Okay, so one way we can describe these things is using payoff matrices or like a table. So if we think about prisoner A and their options versus prisoner B, and one of those would be to cooperate. And by cooperate here, I mean cooperate with each other. And the reason I'm calling it cooperation here is more so that it links in well with the evolutionary side of things. Cooperate with each other, meaning, they're not going to snitch, or defect. Defect meaning that they'll collaborate with the police, the authorities in this case. Okay, so we can write a table. We can think about what is the payoff in each of these different scenarios. So, for example, if we're talking about something like a prison sentence, perhaps if they, let's see, this table, just notation-wise, the payoff, you would typically think of what's going on the left-hand side as being player one. And so this element here will be the payoff to prisoner A. We'll talk a little bit more about how we set up payoff matrices. This is actually a symmetric game, so it doesn't matter, but we'll be talking about some different variations about this either on Wednesday or next week. So there's a couple of different ways of doing payoff matrices. I just wanted to make that clear. But here, for example, suppose if they both cooperate, in other words, they stay silent, they both get a sentence of, say, 2 years, or perhaps they could even go free. But let's suppose there's a little bit of evidence and they both get 2 years, they get a shorter sentence. If they both defect, in other words, if they both snitch, then they're both going to get a longer sentence, suppose 5 years. And then suppose, say, prisoner A defects and prisoner B doesn't. Then in this case, A goes free. So they've defected, well, you think they're sort of snitching on player A is snitching on player B. And B gets, in this case, say 10 years. And then in the top right box is just the reverse. So B goes free. And A gets 10 years. So the question with this is, what should you do in this scenario? And this is kind of like some of the big insights of game theory. Well, ideally, if you look at this, you say, well, we should surely just cooperate, right? Cooperate, that's the guaranteed, we only get 2 years. That's like the best net outcome for everyone. However, suppose the other person cooperates. Well, the best thing for you to do, suppose we think about this, this column here. So prisoner B, suppose they're cooperating. What's best for you? Well, if you cooperate, you get 2 years. And if you defect, you get 10 years. Oh, sorry, they get 10 years, but you go free. So here you get 2 years prison, here you go free. So the best thing for you to do, in this case, is to defect. And what about if they defect? Well, if they defect and you cooperate, you get 10 years. If you both defect, you get 5 years. So again, the best thing for you to do is defect. So regardless of what the other person does, the best thing for you to do in this scenario is to always snitch. Even though that's not like the optimal of the system, right? The optimal best thing for both of you together is for you to both cooperate. And this is the classic issue in cooperation in an evolutionary sense, because the best thing for a population might be for everyone to cooperate, but often there are incentives for individuals to cheat or defect. Yes.
That's perspective from prisoner A.
This is, yeah, I mean, this is symmetric in the sense that here A goes free and B gets 10 years, or B goes free and A gets 10 years. And yeah, this is if you, yeah, this is from A's perspective. The best thing to do is to defect. The best thing for, if I do it over here, the best thing for prisoner B to do is this column here, right? So they should always defect as well. So if you can't plan with the other individuals, you should always defect. This sets up lots of interesting things when it applies in an evolutionary context, because it suggests, like, when should we expect to see cooperation between individuals? Well, maybe if there's some kind of signaling that goes on. So you can signal to other individuals that you're going to cooperate. And then there raises questions about, well, is your signaling honest or is it dishonest? There's lots of things in evolutionary biology about, are you being an honest individual when you're you know, perhaps saying that you're going to invest in offspring. So suppose male mates with a female, they kind of indicate to each other that they're going to, you know, equally invest into this offspring, but are they being honest about that? So lots of questions arise from this in an evolutionary sense as well. One of the key things is that in game theory, the classical game theory in economics, is that individuals are assumed to behave rationally. Okay, so by that we mean that they're rationally behaving in their own self-interest. They don't care about, you know, others' payoff. They only care about their own payoff. And they want to maximize that expected payoff. So they don't want to do anything where they say, well, okay, I care about prisoner B here, and so therefore I want them to have a lower sentence. This is all about what your own benefits are. And the nice thing is that that translates really nicely to evolution. This is where evolutionary game theory comes in. It applies the same kinds of ideas about decision making, but instead of rational individuals, we're dealing with populations, and instead of a payoff, we're dealing with fitness, or at least the idea of payoff translates very nicely to fitness. So you care about your own fitness, not what's going on in terms of the overall fitness of the population. It's, like I said earlier, it's very good for applying to ideas about, say, animal behavior. So things like mating decisions comes into that. Things about, say, competition for resources or territory. We can also think about these strategies as being a little bit more broadly applied as well. So we could say, should individuals choose, well, choose in the loosest sense of the word, to produce more sons or daughters? That choice may be determined by your underlying alleles in terms of your genetics, but we can think of evolution acting here to, in terms of this choice as being manifested as a phenotypical strategy sort of level, but ultimately we don't need to worry about the underlying details that are causing that choice. We just care about the outcome, okay? So we can determine which strategy might be optimal and under which conditions. And typically, because we're thinking often about interactions between individuals in a population, it matters what strategies other people are playing or other individuals. And so selection is usually frequency dependent. So remember, we did a few frequency dependent models in our population genetics section. In those frequency dependent models, our fitness, for example, we had like WA is equal to P or 1 over P, things like that. So the frequency of a particular allele in the population would affect its fitness, and it's the same thing here. The payoff may depend ultimately on what strategies others are playing. Okay, so what we're going to do today is we're going to go through a classic example of this called the hawk-dove game. Has anyone heard of hawk-dove game before? No? Okay, that's good. Something new. Okay, so like the classic example of evolutionary game theory, or EGT, is in animal contests. And this is a really good example of this. So suppose individuals in a population are competing for some resource, and this resource is limited. Maybe it's food, maybe it's territory, maybe it's mates. And gaining this resource leads to an increase in fitness. You know, either you're able to survive longer and produce more offspring, or you produce more offspring immediately. Ultimately, there's an increase in fitness. Okay, and we're going to assume that this increase in fitness is given by some value B. Okay. And I haven't got it on here, but maybe I think I probably should say this is B is greater than 0. That might come back and bite me, but I think it's this should be positive. Okay. However, during a contest, an individual may be injured. Okay, so this is where this strategizing choice needs to be made. If they are fighting over this resource, they could be injured, and it has a fitness cost C. Again, we'll call C net positive in this case. Hopefully, again, that won't come back and bite me. One thing that individuals can do is they can display without cost. So in other words, they can kind of pretend that they're going to fight, but they don't actually go through with it. If challenged, they'll retreat. So there are two strategies in this hawk-dove game. The hawks always attack. So they're, regardless of what's going on, they're always just going to attack. The dove, they'll display initially, but retreat if attacked. I don't actually know which order it came in, but whether this influenced the economic ideas and also ideas in terms of like foreign policy as well, or whether those are the reason why this is called the hawk-dove game. But you might hear, say, Bank of Canada being hawkish in terms of how they're approaching their interest rate decisions, or they might be feeling more dovish. And likewise, people would be seen as foreign policy hawks because they want to interfere in foreign wars, or they're dovish because they don't want to interfere. Okay, so these things link into other ideas as well. I don't actually know the order in which they came. Okay, so this hawk-dove game, we've got these two strategies, and we want to come up with a payoff matrix. So like the prisoner's dilemma, we want a 2x2 matrix that's going to tell us something about the payoff to other individuals depending on the interactions they have. And because there's two strategies, we're going to have a hawk, 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 dove, dove, hawk, or dove, dove. Those are the possible interactions. Okay. So what we're going to do is we're going to define Aij as the payoff. And when I say payoff here, because we're talking about evolution, we're going to be thinking about this as a contribution to fitness. This contribution could be negative because there might be other things that will be coming together to your fitness. So this payoff or contribution to your fitness is the contribution to I's fitness when an opponent plays strategy J. And we're going to let P be the frequency of individuals in the population who are playing the hawk strategy. And we're going to suppose that individuals encounter opponents with the same strategy. When they do that, they have a 50-50 chance of winning the resource. So for example, those pigeons, they are pigeons, sometimes it's called a pigeon game. The doves, they can display, and the other individual might retreat if they're a dove, in which case they would win the resource, but there's a 50-50 chance that one of them will stand down. Likewise, if two hawks are competing, they've got a 50-50 chance of winning that fight and 50-50 chance of losing it. Okay, so we can write down payoff matrix, just like we had before. So here, A, our payoff matrix. I'm going to write hawks and dove, H and D here, just to make it clear where these payoffs are coming from. Let's move this over. So if a hawk encounters a hawk, their expected payout from that or payoff from this interaction is going to be the benefit, which is B, minus the cost, C, and they have a 50-50 chance of winning. So it's going to be a half of that. So B is the payoff it gets if it wins, C is the payoff it gets if it loses, or minus C is the payoff it gets if it loses, and has a 50-50 chance of winning or losing. So half times B times minus C. If you're playing hawk and you encounter a dove, then in this case, your payoff is going to be B. So I'm going to write this payoff in terms of, like say, Aij is going to be the payoff to the individual on the rows against an individual playing something in the columns. When we come to a different type of game called an asymmetric game, we'll write the payoff matrix in a slightly different way. You could write these in a symmetric way by having two things in each cell, but we won't do that here, just for brevity. Okay, if a dove encounters a hawk, what's its payoff? I think you're mouthing it then, Mark. 0. Okay, yeah. So it displays, but then it retreats. It doesn't pay a cost because it doesn't fight. And then if a dove encounters a dove, what's its payoff? Yeah, half of B. So 50% of the time they win the resource, but they never fight over it, so there's never a cost. Okay, so like I said, this is an example of a symmetric game where the payoff is the same for each player. So we could just flip those rows and columns. They each have the same strategies available to them, and they have the same payoffs for those. So the contribution to fitness for an individual playing a given strategy will depend on the payoff against each type of opponent, weighted by the frequency of interacting with that opponent. So we're going to assume we've got a large population, individuals are just mixing randomly here. So the probability of them coming into contact with a hawk is going to be the frequency of hawks in the population. So all we need is a weighted sum here. And we're going to assume that for our hawks, their fitness, which I'll call WH, is going to be whatever their baseline fitness is, which I've called here W star, plus, wow, their payoff when they come into contact with another hawk, it's going to be a half times by B minus C. So we'll have a half times by B minus C. And the frequency of hawks is P. So the frequency of coming into contact with those individuals is P, and the payoff when you meet them is half. That's by B minus C. And then the frequency of doves is going to be what? 1 minus P, yeah. And we had up here, the payoff in that case is B. And then likewise for doves, for their fitness WD, they have a baseline fitness W star. If a dove comes into contact with a hawk, they have a payoff of 0. So here we would have 0 times by P plus 1 minus P is the frequency of doves, and they'll get a payoff of B over 2. So we can answer a couple of questions here. First of all, when is the hawk strategy always best? And secondly, when can the two strategies coexist? So I'll get you guys to do this, but just to make sure everyone's on the same page. When do we think that the hawk strategy is always going to be best? Well, let me take a step back. When is the hawk strategy the best?
If we have C or 0, like there's no penalty.
I mean, in a more general sense, like, so we've got these fitnesses here. What does it mean for the hawk to be best?
Then the hawk fitness has to be higher than the dove fitness.
Exactly. So when is it always going to be best? Well, it's going to be always best when it's true for all values of P. Okay, so you need to solve WH greater than WD for all values of P. And then when can the two strategies coexist? Well, for them to coexist, they have to have the same fitness, right? For some value of P that is not 0 or 1. So have a go at solving those two. And I'll come around and answer any questions you might have. Okay, let me go through part 1 just to make sure no one's stuck. Okay, so we want to find when is the hawk strategy always best? Part 1 of this. When is the hawk strategy always best? In other words, we need to find WH greater than WD for all P. Remember, P here is going to be between 0 and 1. Here I'm including 0 and 1 because we don't want there to be any value of P for which this is not satisfied, even at the boundaries. Okay, so we've got our values of WH and WD above. So we're going to have W star plus P over 2 times by B minus C plus 1 minus P times by B. It's got to be greater than W star plus 1 minus P times by B over 2. See, the baseline fitnesses here don't matter. They just cancel out. Okay, so we need to do a little bit of rearranging here. So for example, we can subtract from the right-hand side, we can subtract 1 minus P times by B over 2, subtract that from both sides. And we will then get, we'll get P over 2 times by B minus C plus B over 2 times by 1 minus P. And that's to be greater than 0. And then if we multiply by 2 and expand out these brackets, we'll get PB minus PC plus B minus PB. It's got to be positive. These PB terms are going to cancel. So you have minus PC plus B has got to be greater than 0. Or in other words, P has got to be less than B over C. So this is the relationship between P, B, and C. Well, we want this to be for all values of P. P is between 0 and 1. So hence our hawk is always best when B over C is greater than 1 or B is greater than C. For show of hands, who got that? So this shouldn't be maybe super surprising here. If the fitness benefit is always greater than the cost, or if it's greater than the costs, then it's always best to be a hawk. There's no advantage to being a dove. Because whenever a dove comes into contact with the hawk, even if the dove is very, very common, or vice versa, even if the hawk is very, very common, you're still always better off being a hawk. Okay, how about part two? I have a show of hands who's done part two. Okay, I'll just give a few more minutes for you guys to have a go at that. So just a reminder, part two, when can the two strategies coexist? For them to coexist, they need to have the same fitness. So you need to find a value P for which they have the same fitness. Put that just up there so you can see. So this first part here, when the benefits are greater than the costs. So the benefits of this resource, remember we're talking about some resource or think it could be territory, it could be mates, it could be food. When the benefits of gaining that resource offset the costs, then you should play the hawk strategy. And you should always play that strategy. Coexistence occurs when we're going to have the fitness of our two strategies being the same. So WH is going to equal WD. This only has to be true for a particular value of P. So for some P in 0, 1. Can anyone tell me why I have square brackets here and non-square brackets here?
Well, if they're at like a 0% or 100% frequency, then they're not consistent.
Exactly. So for coexistence, we need to have P between 0 and 1 non-inclusive. Okay, so the same as above, we have an equation for WH, WD, and we need to find some P star for which this is satisfied. In fact, I'll call this P star down here. I'm immediately going to drop the W stars because we don't need them anymore. So we'll have P star over 2 times by B minus C plus 1 minus P star times by B. So that's from my WH star has to equal 1 minus P star times by B over 2. So we can do exactly the same as before, subtract 1 minus P star times by B over 2. We'll end up with B star over 2 times by B minus C plus B over 2 times by 1 minus P star. It's got to equal 0. We can multiply throughout by 2. Do a little bit more algebraic manipulation. It's pretty straightforward, so I'll just jump straight to the answer here. We're going to have P star is going to equal B over C. This is very similar to what we had before. Before we had B over C is greater than 1. Really all that matters is this B over C. If B and C are equal to 1, sorry, B over C is equal to 1, so B and C are equal to each other, then we're just at that boundary. But as B decreases relative to C, then all we've done is we've just shifted into this realm where P is between 0 and 1, and therefore they're coexisting. The other way of writing this is you need 0 less than B over C less than 1, or simply B to be less than C. Again, shouldn't be surprising that these conditions butt up against each other. When B is greater than C, you should always play the hawk. When B is less than C, there'll be some value of P between 0 and 1 where they can coexist. Any questions on any of that? Yes.
This whole thing you're talking about expectations and nothing to do with risk and deviation of factors. Like there can be scenarios where my fitness is too low, but even though the expectation is good for me to play the hard, but if I lose, I might go extinct. So that is not a good strategy.
It's an interesting point of using the word extinct. Can I put a pin on that and come back to it a little bit later, just because you raise a very good point, but I want to get to it in a couple of slides' time. So hold that thought. Any other questions? No? Okay. So note that the equations for our hawk and dove fitness are just linear in P. So we can draw straight lines to look at this geometrically. Okay, so if we think about, first of all, the case where B is greater than C, and we think about what is going to be the fitness of our strategies, let's make that a little bit smaller. We have the fitness of a particular strategy, and we're going to plot this against the hawk frequency. P. And for ease, I'm just going to copy this. So I'm going to draw two graphs. Okay, so what do we know? Well, when P is equal to 0, we're just going to be, the hawk is going to be at W star plus B, and the dove is going to be at W star plus B over 2. So if W star plus B, W star plus B over 2, that's going to be the same for both of these. Those are going to be our intercepts. And these are both linear. We know when B is greater than C that the hawk fitness is always greater than the dove fitness. So in this scenario here, if green is my dove fitness and red is my hawk fitness, we have something that looks a little bit like this. For any value of P we're choosing, this is going up to 1, 0. Any value, the hawk is always better than the dove. Whereas when we have B less than C, we know that we'll have a scenario that looks more like this. So although the fitness of both is decreasing, there'll be some P star equal to B over C, where the optimal strategy changes. Note here in this scenario, the hawk, even if it's very, very rare, can always invade the dove. And that's also true here. This is a bit like the cooperating and cheating kind of thing. If everyone else is, this cooperation here is not quite true because they're still competing over something, but if everyone else is playing this dovish strategy, then you can swoop in as the hawk. Everyone you meet, you'll be able to get all the resource from, so that's why your fitness is so much higher. As the frequency of the hawks increase, note that all of these lines slope down. So the fitness of everyone in the population is decreasing as the hawks increase in frequency. In this scenario here, even when the hawks are everyone in the population, doves can't invade. But over here, they can invade. One thing about this, this second scenario, incidentally, just a quick, before I go on to that. We refer to individuals that when they're playing a strategy all the time as it being a pure strategy. So playing hawk all the time or playing dove all the time is a pure strategy. Likewise, if we talk about the optimal strategy here is always hawk, and therefore that is a pure strategy. Over here, optimal strategy is a mixed strategy because there is a mixture of hawks and doves. And there is actually a couple of ways we can interpret this in a 2x2 game. One is that a proportion of individuals P star always play hawk, and they coexist with a proportion of the population 1 minus P star that always play dove. Or, oh, what's happened there? Here we go. The other interpretation is that everyone plays hawk with probability P star per contest. So in other words, everyone's carrying around a random number generator that gives you a value between 0 and 1. They hit that random number generator at the start of each contest. If that number is less than P star, they play hawk. If it's greater than P star, they play dove. They can't see each other's random number generators, by the way. That would confuse things a little bit. So generally, we think about mixed strategies when it comes to game theory as being this latter one here. And that's because it's more general. It turns out that as soon as you have more than two strategies, these two things no longer mean the same thing. So generally, we think about this as being a probability distribution where every individual can play one of the two strategies. Either they play hawk or they play dove, and they're essentially rolling a dice or looking at random number generator to determine what their strategy is going to be. Like I said, this first one also can be seen as two sets of individuals playing pure strategies, whereas the second is a set of individuals playing mixed strategies. Really, they both should be seen as mixed strategies. In future, I'll be referring to pure strategies as this kind of scenario here. This is a pure strategy for hawk, and I'll refer to this as a mixed strategy. Right. Okay, the last thing I want to go through today is thinking about Joan's question. Sorry, yeah. Okay.
My understanding was that we do not have two different species. We have a species, but we have two different like kind of gene.
Yeah.
One makes you play the hawk, and the other is playing dove, and we are going to figure out which one is going to like become dominant, or like overtake the other, and the frequency of these two. But in the second case, if we talk about everyone playing something with the same probability, I can't understand what's the meaning of talking about different fitnesses, because everyone is the same. We can't divide into two different groups.
So yes, in the sense that in the first one here, you could imagine, I sometimes think of this as being like, say, two strains of bacteria, and one plays the hawk strategy, one plays the dove strategy. Bacteria are nice and simple to think about because they're asexual. So those two bacteria would coexist. The second one, there is still a population of bacteria this time, but now they are genetically uniform. But each time they interact with each other, there's a probability that they will do behavior X or Y, hawk or dove. Okay, so there's still one species there. It's just there's a probability associated with their interactions. So
it means that we cannot group them and talk about the frequency of group 1 and group 2.
No, in that sense that this P becomes just the frequency of, or the probability of playing that strategy amongst the individuals, among the whole individuals, yeah.
Yes, but I mean the whole discussion will be nonsense, because
no
groups that we want to study their frequencies, like.
But no, not necessarily. No, but you're not interested necessarily in the frequency of those groups. You're interested in the frequencies of the strategies. So if you examine, so in this mixed strategy scenario, if you go and examine a population, you would expect to see the hawk strategy played a proportion P star of the time. You don't care about who's a hawk and who's a dove. You care about the strategies themselves.
I mean, the factor that should decide is the competition of this whole bacteria versus something else. I mean,
no, I mean, evolution occurs, natural selection occurs within a population, right? You're competing with other individuals of the same species.
So we should find the optimal P star for which the whole fitness is the maximum.
That's what we're getting onto now. There's a slight difference there in terms of those two things. What is good for the individual is not necessarily what's good for the population or the species. And that's what I kind of wanted to drive at now. So you had a question earlier, and I wanted to make sure I address that. So let's think about the mean fitness of the population. So mean fitness is just going to be the frequency of hawks, P, times by the fitness of hawks, plus the frequency of doves, 1 minus P, times by the fitness of doves. And when I'm saying hawks and doves here, I mean the strategies themselves. Note that both of our fitnesses, remember, are linear in P. And therefore, our mean fitness is going to be quadratic in P. So it's going to be maximized when mean fitness of the population is going to be maximized when we take the derivative of mean fitness with respect to P, and we set that to 0. Okay, we want to find the maximum fitness of the population. This is what you were just asking about, right? When's the fitness of the population maximized? Well, in this case, if we take the derivative, so we're going to have P times by the fitness of the hawks. So we had before a W star times by P now. So when we take the derivative, it's just going to be W star. And then if I just go back up here to make sure it's clear, so I'm taking the derivative of P times by this. So I'm going to have a P squared over 2 term. And I take the derivative of that, I had a P squared over 2 times by B minus C. The 2 is going to come out the front, cancel. And then I also had a 1 minus P times by B. We're going to multiply this by P and then take the derivative. So we'll end up with a 1 minus 2P. And then similarly for the dove, we had a W star before. Sorry, that will be cancelled out. The W star before is now getting multiplied by P. And so we just have something that's linear, so that we keep the W stars, but also they cancel out here because we've got a plus W star and a minus W star. And what else do we have? We are going to have minus, we'll end up with a minus 1 minus P all squared times by B over 2, because we're multiplying the second thing by 1 minus P. Take its derivative and we'll cancel, the 2 comes out the front and then cancels here. And this is all going to be equal to 0. So all I've done there is I've taken this expression for W bar, multiplied the first term by P. So sorry, multiplied WH by P, multiplied WD by 1 minus P, and then taken the derivative with respect to P. Okay, so what are we going to have here? If we expand everything out, we will get PB minus PC plus B minus 2PB minus B plus PB is equal to 0. We're running short on time, so I'll just expand it now.
Plus, this maybe on one for the second time, because it's P times WH plus 1 minus P times WH. And then you keep the derivative of W star.
Yes, we're gonna have a minus coming out the front because there's a minus P here.
Oh, after the derivative.
After the derivative, yeah. Okay, so just a bit of cancellation. Time's running short, so I will go through this fairly quickly. The PB's terms are going to cancel. The B terms are also going to cancel, and we're going to end up with minus PC is equal to 0. Now, remember earlier I said that C was greater than 0, so this means that P must equal 0. In other words, no hawks. That shouldn't be too surprising because if we go back to these graphs here, the fitness of both of our strategies, individuals playing both of these strategies, decreases as the frequency of hawks increases. The mean fitness of the population, therefore, is maximized when everyone is a dove because there's no costs, right? You have a 50-50 chance of getting every resource, but you never pay a cost of getting injured in any of these contests. So why did that matter? Well, we see in both of these strategies, when P is equal to 0, the hawks are able to invade. So even though the population is at its maximum fitness, the hawks are able to invade. But as they invade, they reduce the fitness of the population. So this again links back to ideas about cooperation and cheating in a slightly different context, but the same principle of what's good for the population isn't necessarily what natural selection will favor. Natural selection here will always favor hawks, even though it decreases the population, the fitness of the population, because it's good for hawks. So I'm not going to write that up reading it, but here I've got it in the notes online. But basically what I've just said now, the mean fitness of the population is maximized when the hawks are not in the population, when everyone is playing dove. But the optimal strategy is either to always play hawk if B is greater than C, or a mixed strategy of playing hawk a proportion P star of the time, and that P star is equal to B over C. And that's if B is less than C. So in both cases, evolution will always reduce the mean population fitness, and typically we would expect that to reduce mean population size. And so we would expect things like the population size to be lower. So this is a really good example demonstrating that evolution does not necessarily do what is good for the population. That's a really important principle to maintain going through everything that we're going to do, even when we go beyond evolutionary game theory, the idea of not falling into the trap of evolution will favor what is good for the species, or evolution will favor what is good for even a population, not even at the species level necessarily. Okay, so we need to think about what's going on, what is good for an individual. The ideas about cooperation and cheating as well. You can think about things in terms of like overfishing is another example, or climate change. Now, what would be good is if everyone like agreed to cooperate on these things. So for overfishing, you stick within your quota. With climate change, everyone agrees to stick with, reduce their carbon emissions because that would be good for everyone, right, as a whole. But individually, it pays to overfish because you get your immediate profit. With climate change, it pays to have not have carbon taxes and things like that, not green your economy necessarily because you can just get away with cheap coal, things like that. So that's all of these ideas about cooperation and cheating and defecting and so on. They all kind of link together to say things that are good for the population as a whole and not always what's reflected because of individual advantages. And the same thing happens for evolution. Okay, that's it for today. That's just a summary there, just summarizing what we've done. We're going to be talking more about evolutionary game theory on Wednesday, looking at some different scenarios. Okay, thanks everyone.